today's sessions we are going to discuss analysis of an amplifier using H parameters. The objectives of this session is a definition of H parameters in common base, common emitter, common collector configuration, and relationship between common collector and a common emitter amplifier, and exact analysis of transistor amplifier using H parameters. The figure 2a shows that a common base configuration, that corresponding hybrid model as shown in that figure 2b. In the previous class we discussed that a H11 is equal to Hi and H12 is defined as an HR reverse voltage gain, and H21 is to be defined as HF, that is forward current gain, and H22 is defined as H0, output conductance. For this model we defined a Hi is multiplied with HR V2, on the other side this is HF is multiplied with I1 is a constant current source and is in parallel with on H0. This is to be 2 dash and 1 dash. For this model we have to add a suffix, second suffix for the common base, common emitter, common collector configuration. Here this for the transistor, that a 1 dash and 2 dash is common for both input and the output, where that 1 dash and 2 dash is replaced with either B or E or C. For a common base configuration as shown in that figure 2a, then its equivalent circuit is given by, we have to add, this is a base, in between the base there is a transistor input resistance, that is HIE, and is followed with a voltage source plus minus, that is HRB into V B. This is your emitter, and similarly output terminal, this is a constant current source, this is HFB IB, and is followed with, this is HOB, it is a conductance, and then this is a collector, and then this is your base, this is your emitter, and then this is your base. Current flowing through this is IB and current flowing through this is IC. Then voltage across this function is given by common emitter base junction VBE, and output is to be taken across VCB. Then based on this equivalent circuit diagram we can define that a input equation, that VBE is given by that current HIB is multiplied with IB plus HRB with VCB, HRB is multiplied with VCB. And similarly if you are applying KCL at this node, then the collector current IC is given by HFB IB plus a current voltage across, this is nothing but HOB into VCB. This is a one set of equation for a common base configuration. Similarly for a common emitter amplifier as shown in that figure 3a, in this circuit we shown that that input current is IB, output current is IC, emitter is common. Then its equivalent circuit is given by the add a second suffix E, then this is multiplied with HRE with VCE. The input is base between, and then voltage across, this is nothing but VBE, this is VEB. And then here we can define the constant current source HFE IB, output is to be taken as HOE, output is between the collector and a emitter, and the voltage across this point is VCE. If you are applying KVL to the input base circuit, then that is equal to VBE is equal to HIE IB, and voltage drop across that constant current source, that is nothing but HRE VCE. For the output collector means current flowing through this is your IC, applying KCL to this node, then that collector current IC is equal to H FE IB plus HOE VCE. We will call this equation as 2. Where this is to be defined? Next, you have to defining a common collector configuration. Common collector configuration as shown in that figure 4a, then that corresponding the hybrid equivalent model is given by collector is common for both input and the output. The input current is as shown in that figure, input current is IB, output current is IE, where this equivalent circuit of this common collector configuration, that CC, is given by that HIC is with a constant voltage source, that is HRC into VEC. A voltage is between that base and a collector is nothing but VBC, and here we have to define a constant current source, that is HFB multiplied with IB input current and a constant voltage resistance, that is HOC with a collector current E and C. Emitter current normally it leads outside, leaves, then the voltage across this is nothing but VEC. Here this point is common for both input and the output. Then the corresponding equations for this input side and output side is given by VBC equal to HIC IB plus HRC VEC, and a KCL at this point IE, E is equal to HFB IB plus HOC VEC. This is a set of equation 3. Means we defined here that a constant hybrid parameters for a voltage, a common base, common emitter and a common collector configuration. Next, what is the difference between these two? Then is it necessary to analyze all the 3 circuits, or if you are remembering only one circuit, one set of equation, is it possible to link? For this we need to determine that relationship between the common emitter and a common collector configuration, a common emitter and a common base, and a common emitter and a common collector and a common base configuration. Means you have to finding the relationship between CC and CE configuration. For the relationship between CC and CE configuration, we need to define, either you have to modify the equation, means equation 2 or equation 3. Means using the basic concepts, we know that already IE is the outward current because it leaves, therefore you can write this is nothing but IE is equal to minus of IC plus IB. In the other side, that input both current, 2 currents are enter and other current is leaving, here that emitter current is also entering into this circuit. Then also we know that from this transistor we defined that voltage current relation already in the previous class. We defined this is this junction voltage is nothing but VBC, this junction voltage is nothing but VBE, and then this junction voltage is nothing but VCE. Then if you are reversing the polarity, then you are going to get minus of, this is also defined as minus VEB, this is minus VCB, this is minus VEC. If you are substituting this voltage and current equations in this expression, and then you have to finding the relation, either you have to modify that equation 3 or modify equation 2. Means from this equation it is clear that if you substitute a VBC is equal to, if you are applying, means VBC means you are applying, this is plus, this is minus, applying KVL to this path, then VBC is equal to VBC plus to minus VBE minus VCE equal to 0. Then VBC is equal to VBE plus VCE. But your equation required is on VCE in terms of, therefore you are going to get VBE and VCE. This equation is also in terms of VBC. Therefore we have to modify this VEC, where VEC equal to minus VCE. Substituting these into the equation 3, then you are going to get VBC is equal to VBE plus VCE. this is VBE plus VCE equal to HIC IB plus HRC, because VEC is equal to minus VCE, therefore, this becomes minus HRC into VCE. And similarly, if you are solve for, because this equation 2 represents an solve VBE, therefore, you have to solve for VBE, then this is equal to VBE is equal to HIC IB. If you transfer into this side, it is going to be negative, you have to take minus into 1 plus HRC into VCE. One thing. Second is you have to modify this equation, that I is equal to minus of IC plus IB. Therefore, you are going to get minus IC minus IB equal to HFB IB minus HOC VCE. You have to multiply, you have to shift and then solve for collector current IC. Then you are going to get this is equal to IC equal to minus IC is equal to HFB IB plus IB minus HOC VC. Then IC is equal to minus of 1 plus HFB minus into minus plus HOC VCE. You are calling this equation as 4A, this equation as 4B. If you are simplifying, means you are compare this equation 2A with 4A, 2B with 4B, then we will get the relationship between, then we are going to get the relationship between, because LHS are equal, then these components are IB, currents are equal, then from this you are going to get HIE is equal to HIC and HRE is equal to minus of 1 plus HRC and IC is equal to this, therefore, you are going to get HF is equal to minus of 1 plus HFB and HOE equal to HOC. This is a relationship between a common collector and a common emitter configuration, where this is equal to HIC IB minus HRC. Okay. This equation means, if you remember that any one set of equation means either HIE, HRE, HFE, HOE, we can able to determine that a common collector configuration. Similarly, we can find that relationship between a CE and CB and also CC and CB. Already we specified when we are discussing the hybrid parameters that what are the advantages of this hybrid parameter. The advantage, what are the advantages? Advantages means that output impedance is identified, means we can able to get, and input impedance is accurate. Hence, the advantages are means this transistor H parameters are obtained for a set of values are in a accurate in a particular region. Then the next question is whether these parameters are constant. What is the effect on these parameters, H parameters? Later we will discuss the values. Either these values are constant or variable. For this question, answer is, means in this comparison of this H parameters, we defined that input for a different configuration CB, CE, CC, that HIB's definition is VEB by IE, VB by IB, and HIC is equal to VBC by IB. Similarly, that HRB, HFB, HOB. In general, we can defining that you have to finding this ratio is nothing but an input and voltage and input current and output voltage and output current, the relation. And H parameters of this table shown in figure 2, that HI, HR, HF, H0. You have not added the second suffix, where the second suffix in this case indicating that a corresponding configuration. In general, that HI for a common base configuration is 21.6 ohms and CE is 1.1 kilo ohms and CC is also 1.1 kilo ohms and HR is 2.9 into 10 to the power of minus 4 and CE is 2.5 into 10 to the power of minus 4 and HR in case of the common collector configuration, it is a emitter follower that approximately equal to 1. and HF in case of this is minus 0.98, and CE configuration HFE is 50 and CC is minus 51. H0 is 0.49 into 10 to the power of minus 6 mhos. It is H0 is a conductance, then its reciprocal is a resistance. Then you have to calculate a common emitter configuration 24 into 10 to the power of minus 6 mhos and 25 into 10 to the power of minus 6 mhos for the common collector configuration. Next question, already I specified why now these parameters are constant. Because we know that the input current, input resistance and all impedance is to be depends on either IC, IB, IE, and similarly it depends on VBC, VCE, VBE and VCE. We know that for a transistor that a input current for a common, with respect to the common emitter amplifier, a input voltages are IB and the input current, and VB is the input voltage, and for a common emitter configuration output is collector current is the output current and VC is the output voltage. Means if these values are constant, if and only if these junction parameters are constant and VBE and IC, these are depends on this, means HIE, HRE, HFE, HOE are depends on that junction voltage and a junction currents. Then what is the relationship between that? Because we have to see that already we know that a temperature varies, increases. As the temperature increases, a reverse saturation current ICO is also increases and VBE decreases. Means as the by definition HIE is equal to delta VBE by delta IB. This input current IB is depends on the applied voltage, but this VBE is depends on the junction voltage. Means as the temperature increases, that VBE means decreases at the rate of minus, means a 7 millivolts per degree Celsius. Means if you plot a temperature versus, that means with a parameters values, this value means input resistance is decreases, means HIE is decreases as the voltage increases, because this VBE is decreases, means this is a decreases like this HIE value. And similarly that HRE is to be defined as delta VCE by delta VBE. We know that VCE is independent, but VBE is depends on the temperature. For this, a change in voltage, once again that VBE decreases as the temperature increases, VBE is decreases, hence HRE is increases. Therefore, that HRE is to be increases like this exponentially, because it depends on the temperature. And the HFB, HF is equal to delta IC by delta IB. This IB is depends on that input voltage, but this IC is to be depends on, where we know that IC is equal to HFE beta times IB plus 1 plus beta times ICO. If you are assuming that this beta is constant of a transistor, means that beta is nothing but relationship between the change in the charge carriers in the collector to the change in the charge carriers of a base. If that beta is constant, if this beta is constant, then IB is also depends on the input voltage. You are assuming that this is also constant. When this ICO is increases, it doubles for every 10 degree rising. Therefore, HFE, as the temperature increases, that HFE is also increases. And last parameter is HOE, where HOE is given by delta IC by delta VCE. Once again, as the temperature increases, the ICO increases, that HOE, because VCE is independent of the temperature. As the IC temperature increases, ICO increases, delta IC is also increases, HOE is also increases. Means as the particular, means these are the values that the H parameter values are varies as the temperature varies 1 point. As the, if you are keeping the temperature constant, means you have to maintain the room temperature is constant or a temperature constant, then under the constant temperature these parameters are constant, and then this analysis is more accurate. This is one value. Other parameters are, it also depends on the IC, because whatever the values given in this table is specified at a particular current, IC is equal to 1.3 milliamperes. means if the collector current IC varies, then H parameters are also varies like a temperature. Means we are discussed the various configuration hybrid parameters and relationship, and then a variation of that hybrid parameters with respect to the temperature and a current. Then we have to discuss on advantages. What are the advantages with respect to the RE model? That H parameters are real numbers up to a radio frequency, means these H parameters are remains constant even at radio frequency, means at few gigahertz, and these parameters are easy to measure, means you can be able to measure by using a transistor characteristics, and the H parameters can be determined from the transistor static characteristic curves. They are convenient to use in circuit analysis and design, because these H parameters are not depends on the external components, it is depends only on the transistor parameters. Therefore, these values are almost constant, easily convertible from one configuration to the other. We are shown with one example, and readily supplied by manufacturer, means if you refer a transistor, if you purchase any one component, for example SL100 or AC127, if you purchase this component SL100 or AC127, means if you refer the data sheets, these H parameters are given in the table or a data sheets. Next, let us consider a common emitter transistor amplifier analysis. Means in a common emitter transistor amplifier, means if you are consider a linear network, this network consisting of a transistor. Transistor means normally we are used as a common emitter configuration. This transistor is supplied with a external source voltage Rs, and then 1 dash, and the input applied is on Vs. Output is to be taken across a load impedance ZL, and then this output voltage is nothing but V0. Current flowing through this I0 is flowing in this direction. This is your I2, this is your I1, and voltage at this point is V1, and voltage at this point is either V2 or 2 dash, this is V2. Then this a linear network can be analyzed by replacing transistor with its equivalent model. For its equivalent model means you have to replace this block with its equivalent, means instead of a transistor CE configuration in general, you have to consider for a general amplifier. In a general amplifier, that input side there is a resistance HI, and then HR, V2 or V0 we can consider, and then the other side this is HF into I1 the current, and then this resistance is H0, and then this is 2 dash. For the across the terminal 1 dash, that input is applied with its source resistance Rs is taken into the account, and then this voltage is Vs. Voltage at this point is Vi, and similarly the current flowing through this network is I2, and then that output impedance is ZL, and then current flowing through this is I0, and then voltage across this is V0. Okay, means here the transistor is replaced with its equivalent circuit diagram as shown in this figure. The analysis of this transistor amplifier means we need to calculate a current gain AI, voltage gain AV, input impedance Zi, output impedance Z0. And also apart from that, we can be able to determine that current AIS and a voltage gain AVS. We will discuss and derive an expression for these parameters one by one. If you are consider means input impedance means you are looking into the input terminals of a transistor, it is known as a ZI. Output impedance means you are looking into the terminals into the 2 dash, and if you are consider that ZL, then you have to consider this output impedance is Z0 dash. First let us consider the current gain of an amplifier. Current gain AI is given by I0 by I1, I0 by I1. Okay, I1 is the current flowing through the input terminals of a transistor, and I0 is the output current. Means you need to find that relation I0 by I1, you have to find first I0. I0 is equal to minus I2, because these two currents are leaving from this node, and then where I2 is equal to sum of the current, that current flowing through this is given by HF I1, and this H0 is the conductance. Therefore, already we know that voltage up across this resistance in conductance is nothing but V0. The current flowing through is nothing but H0 into V0. Then what is V0? V0 is nothing but I0 into ZL, where I0 is equal to minus I2. Therefore, this is equal to minus I2 by ZL. You are going to get this is equal to, substituting into the above expression this equation 1 and 2, then I2 is equal to HF I1 plus minus I2 ZL into H0. I2, if you take on this one into this side, then you will get Y2 into 1 plus ZL H0 equal to HF I1. Hence, that current gain is AI is equal to I0 by II. This is also equal to minus I2 by I1. From this equation, that ratio is given by minus HF divided by 1 plus ZL into H0. These equations are helps to solve a numericals. Now, once you have to find an input current gain is to be depends on that a short circuited current gain HF, and then it is also depends on the output load or a load impedance and the output conductance H0. Input impedance Zi, where input impedance Zi is to be defined as that you are looking into the terminals 1, 1 dash. Hence, you are to defining that input Zi is equal to Vi by Ib. You are because where that a source voltage Vs is along with that internal resistance Rs. At this moment, you are assuming that Rs is 0. Therefore, you are going to get Zi is equal to Vi by Ib. For this equation means you are looking into the 1, 1 dash, then you have to finding this ratio, applying KVL to this path. When you are applying KVL to this path, Vi, okay, this is plus, this is minus, and then current flowing to this is nothing minus HI I1 minus HR V0 is equal to 0, where V0 is given by minus I2 into ZL, where V0 is equal to minus I2 into ZL. Okay. Substitute this into the above expression, you are going to get Vi equal to HI I1 plus HR V0, where this is nothing but HI I1 minus I2 ZL into HR, where this Zi is nothing but Vi by I1. Hence, you have to divide both the sides by I1. you are going to get Vi by I1 is equal to Hi minus I2 ZL HR by I1. We know that a minus I2 by I1 is nothing but a current gain Ai, hence Zi is equal to Hi plus a I2 by I1 is nothing but current gain Ai ZL HR. Means a input impedance of a transistor amplifier is depends on that a hybrid short circuited input impedance and a load resistance ZL and the reverse voltage open circuit reverse voltage gain HR. Next, we have to determine the voltage gain. That voltage gain AV is equal to V2 V0 by Vi by definition, means where V0 is the voltage taken across the ZL and Vi is the voltage applied to the terminal 1 1 dash. From this circuit, means from the definition of an circuit diagram, we know that this V0 is equal to minus I2 ZL, and from this a input impedance equation of an input impedance where Vi is equal to Ii into Zi, where Vi is equal to I1 into Zi. Hence, you have to take the ratio of this AV is equal to V0 is I2 minus I2 ZL by I1 Zi, where this minus I2 by I1 is nothing but the current gain. Hence, AV is equal to AI ZL by Zi. Means if you are observing that equation 4 and 5, equation 4 is an equation of an input impedance and equation 5 is represents the equation of a voltage gain. These two, a input impedance and voltage gain, is depends on the current gain of a transistor amplifier. Hence, therefore, if you know the current gain, we can easily calculate the input impedance and the voltage gain. Output impedance. Because we need to determine output impedance, means we are looking into the terminal 2 2 dash. In looking into the 2 and 2 dash, here these two are in parallel. Therefore, this is output H0 is nothing but the conductance, output conductance of a transistor. Hence, we need to determine the Z0 output Z0 or impedance Z0. This can be defined as 1 by Y0. Means we need to determine the output admittance Y0. Okay. When you are finding an output admittance first, then you are looking into the input terminals 2 2 dash. Means here to finding an output impedance, you have to set 2 points. One is Vs is equal to 0, source voltage, and ZL is equal to infinity. Means you have to determine the output impedance across 2 and 2 dash, means you have to open circuit the load and short circuit the source. When this short circuited this source, then what is Y0 when you are looking into this? This is given by Y0 is equal to, this is nothing but ratio of I2 by V2. Hence, we need to find what is an I2, where I2 is given by applying KCL at this point. This is nothing but HF I1 plus H0 V2. That current flowing, it is a where V0 is the open circuited current gain. Hence, you have to divide both the sides, because divide both the sides by and V0, then you are going to get I2 by V2 is equal to H, this is nothing but H0 plus HF I1 by V2. Then what is the relationship between I1 and V2? for this we need to find applying KVL, because we are setting that Vs is equal to 0. When Vs is equal to 0 means this is acting as a short circuit. Applying KVL to this path. Applying KVL to this path means the current flowing through that Rs is equal to the current flowing through this. This current is to be driven by this constant voltage source. Hence, you are going to get this is equal to minus I1 Rs minus HI I1 minus HR V0 is equal to 0. This is equal to minus I1 into Rs plus HI is equal to HR V0. We want that I1 by I2 ratio, where this is minus I1 by I1 by V0 is equal to minus HR divided by Rs plus HI. Means this ratio I1 by V0 or V0 is equal to V2, I1 by V0, hence this is equal to minus HR divided by Rs plus HI. You have to substituting into this above expression, then that Y0 is equal to I2 by V0, this is equal to H0, this I0 by V0 is nothing but minus, therefore minus HR HF divided by Rs plus HI. Means your Y0 is given by this, then that impedance Z0 is equal to 1 by Y0. Means first we need to find the admittance of a network, then you have to substitute that Z0 is equal to 1 by Y0, you are going to get the output impedance Z0, where output impedance is to be obtained that setting that input voltage 0 and output circuit ZL is equal to infinity. Next, if that considering the load resistance impedance ZL, what is the effect on the input output impedance? Because when you are looking into the terminals 2, 2 dash, this entire circuit is to be replaced with a Z0, then this looks like that circuit, this is your Z0 and there is a resistance ZL. When you are looking into the terminals like this, this is your Z0 dash, where Z0 dash is nothing but a parallel combination of this and this, hence your Z0 dash is equal to Z0 plus in parallel with ZL. Means we have determined a voltage gain, current gain, input impedance and output impedance by considering that load resistance Rs into the account and a load resistance ZL into the account. Now, if we consider this Rs into the network and ZL into the network, means either we have consider the biasing network, what is the effect on that a current gain AI and a voltage gain AV, and also what is the effect on ZI, because already we are observed that when you are looking into the, if you are considering account ZL into the account, then your output impedance Z0 dash is a parallel combination of Z0 and Z0 ZL. Then what is the effect on this parameter? When looking into the terminal 1, 1 dash, ZI is remains same, but if you consider, if you are looking into this side ZI dash, what is the impedance, input impedance? Can you guess? Either increases or decreases. Means here due to the a source Rs into the account and that voltage gain AI, AV and ZI, all the parameters are decreases. You have to determine that relation while taking this current gain, voltage gain and with considering the Rs into the account. If we consider the current gain AI is equal to, if you are assuming that current flowing through this is your Is. Okay. If you are considering the current source Is into the account, and then what is the effect on this, because we are assuming that when you are looking into this, this is the ZI. This circuit can be defined as output current gain is to be denoted with AIS, where you have to define current gain AIS while taking that Rs, load resistance Rs into the source resistance Rs into the account, where AIS is given by definition, this is nothing but I0 by Is. Okay, where I0 is nothing but minus I2 by Is. Okay. We know that already, that relation between I2 and I1. This can be defined as minus I2 multiplied and divided by I1 and I1 by Is. Means if you consider this is your AIS. We know that already that minus I2 by I1 is nothing but a current gain of a transistor without a lower resistance Rs into the account. Hence, this AIS is equal to AI into I1 by Is. And how do you determine this? This can be obtained if this is transforming a constant voltage source into the converting into the current source. Means from the networks we know that already means this is the voltage source Vs and its internal resistance is Rs. Then this network, by using a source transformation network, we can transform into the a voltage source or a current source by means this Vs is replaced with a constant current source Is, where Is is equal to Vs by Rs, and then this Rs is in parallel with Is. Means you have to transform this voltage source into the a constant, a current source Is, where Is is given by Vs by Rs. Then in case of a this one, this is Rs is in parallel. This is to be applied to the terminal 1 1 dash. Already we know that when that looking into the terminals 1 1 dash, that impedance is to appear across this point is nothing but Zi, means this is to be defined as Zi, current flowing through this is my I1. Now using the networks theorem, that is a parallel network where I1 is nothing but a total current Is into opposite branch resistance Rs divided by total resistance Rs plus Zi. If you substituting into the above expression, then current gain with a constant voltage source is given by AIS is equal to AI into Rs divided by Rs plus Zi. Means due to the a source voltage Rs, that a current gain of an amplifier is decreases. And similarly for the voltage gain AVS, where a voltage gain AVS is defined as the ratio of the output voltage V0 and Vs. For this circuit, this is given by V0 by Vs. Once again, already we know that this can be defined as V0 by Vi and Vi by Vs, because there is no, because there is a input voltage between them. By definition, this V0 by Vi is nothing but AV and Vi by Vs. What is this? Next question. How do you determine that ratio Vi by Vs, where Vi by Vs is given by, from this circuit, what is the Vi by Vs? Vs is the source and then this is the resistance Rs. This voltage applied to the terminal 1 1 dash. We know that when you are looking into the terminal 1 1 dash, then what is the value? This entire means this, when you are looking into this complete circuit is replaced with an Zi. Hence you are going to get this is the Zi. Voltage drop across this Zi is nothing but Vi. Okay. Now we need to find an output voltage Vi. This Vi is given by, Vi is nothing but voltage drop across this is nothing but Zi, that applied voltage Vs multiplied with Zi divided by Rs plus Zi. Then the voltage gain AVS is given by, this ratio is substituted here, AV into Zi divided by Rs plus Zi. Means from this circuit analysis, we discussed that you are determined that AVS is equal to AB into ZI divided by RS plus ZI. If you summarize this small signal analysis of a transistor, we determine these are the important things you have to remember, that you have to defining that current gain AI is equal to minus HF divided by 1 plus H0 into ZL, ZI is equal to HI plus AI ZL HR, AV is equal to AI ZL by ZI, and Z0 is equal to 1 by Y0 equal to 1 divided by H0 minus HR HF divided by RS plus HI. AIS is equal to AI into RS divided by RS plus ZI, and AVS is equal to AV into ZI divided by RS plus ZI. Means this is a summary of this unimportant equation. Means if you know that a current gain in a transistor amplifier, you can able to determine that input impedance, output impedance, and also that AIS and AVS. Means this is depends on this parameter. This analysis is known as an exact analysis of a transistor amplifier. Next question is how? Then what is the difference between the common emitter, common collector and a common emitter configuration? Because here these are the, there is no second suffix, means here you are derived for a general amplifier without considering either a common emitter, common collector and a common base. Then how do you determine a common emitter, common collector, common? Means wherever that HF, HR, HI, HO, this is to be replaced with a second suffix. For a common emitter amplifier, you have to replace with an HI, HRE, sorry, HFE, HRE, HIE, HOE. And similarly, means that second suffix is indicating that a corresponding configuration, means it is a E suffix is indicating that a common collector or a common emitter configuration. If E is replaced with C, in this case the same equations are useful for the determination of a common emitter, common collector configuration. If it is used add second suffix, then you are going to get a common base configurations. Today's class we considered from the definition of an hybrid parameters and a definitions of the hybrid parameters in a common base, common collector, common emitter configuration, and then you are found also a relationship between that CC and CE, and also we discuss the transistor amplifier. The summary of this as shown in this equation or a box. This helps to solve this. In the next session, you have to consider one example on this, a complete analysis or exact analysis of a transistor amplifier, and then you have to consider approximate analysis of the transistor amplifiers. Thank you.